So that would be the boundary conditions. If you meet that requirement when everything is fast, then chances are you won't have to worry about all the corners. So the concept of corner simulations or corner timing analysis when you implementing a design is key because obviously you cannot just analyze all the corners all the time during optimization. That would kill your runtime. So you pick the worst uh, to analyze during your implementation. Implementation meaning you make a change, you do a quick timing analysis, and then you say, I'm okay. So you use that corner, the extreme corner for your optimization. At the end, when you sign off, you will run whole time analysis on all the different corners, all the different combinations. So when signal runs fast, that means highest voltages. That means the fastest transistors and also the cold temperature. But in smaller nodes, there's a concept of there's a phenomenon called temperature inversion, meaning cold is no longer the fastest. No, I'm sorry, that's on the setup. Never mind. So basically, you just pick the corner where everything is a combination of everything will make the signal travel the fastest. Therefore, that's an extreme corner for whole time analysis. I hope that helps a little bit. Ngô Thái Anh Hào, yeah.
Yes, so thank you, Phil. So think about this from the standpoint. Let's say this is just from interim number. Let's say this is the 5 nanosecond arrival time, the minimum, right? So if this signal here, UD1, if on the slow corner, it may arrive at 8 nanosecond, right? And on that slow corner, you say, oh, actually, it's passed. But on the fast corner, this signal may arrive at 4 nanosecond. Then you actually violate, right? So that's why you want to check it at the fastest corner to make sure that this data is arrived at 5. So at 4 here, so we have to delay the signal to make sure it's at 5. Because on the fastest corner, on the slowest corner, it's arrived later. But when you check the other extreme corner, which is the fastest one, it may be faster. You maybe arrive late, right? So if you check the slow corner, you may pass, but then when you go to the fast corner, you may violate because the data arrived too early, right? So you want to check the absolute worst case for hole would be the fastest corner, right? So if you meet the fastest corner, all the other corners going to be out here. The delay is going to be slower. It's going to be out here. So for sure, you're going to meet, once you meet the fastest corner, the fastest timing library, then you go into all the other corners going to meet. Okay, so opposite is true for the setup. Okay. Okay, so I think we're good on this. Let me get out of.
Yeah, so comment of Ngô Thái Anh Hào as a follow-up. So does that mean setup time must be closed at the slowest corner and the slowest lip?
That's correct. Yeah,
Yep.
remember we talked about setup time where it has to yeah, setup time must be at the worst timer, right here, slowest timer and the worst RC corner, right? So likewise here, when you look at setup time, so the data, if the data arrive, if you check at the fastest corner, the data may arrive here, right? But you check the slowest corner here, so it's basically it's a max check. So it's very it's opposite. So you want to check the slowest corner. It meet here, that means all the fast corner is going to meet because the data can change before, right? This is the latest it can change in terms of the capture edge. So it's opposite. Yeah.
So Ngô Thái Anh Hào, since you talk about setup time, right? So that's when temperature inversion should be noted, meaning that typically when the temperature is high, then your signal is low. But for temperature inversion, the signal is the transistor is lower at the cold temperature. So just some note that the worst case might not be the hot, but might be the cold, very cold corner.
Okay, so good. Okay, so let me get out of this one.
There's another one you want to read and respond.
Okay, so ladies and gentlemen, will we face any cases where we should consider the slowest corner, fastest live, or fastest corner, slowest live? If you, let's see, will we face slowest corner, fastest live? Usually, not in the PD that I'm aware of. In the static timing libraries, when you run STA, they run a lot more corners than we normally run in PD in physical design. There are, let's see, slowest, fastest lab. So I haven't seen the slowest corner, fastest library. There usually fast, min, typical. When we do PD closing, we usually deal with extreme corners. But the STA deal a lot more corner than we do in terms of checking different corner cases. Ping, Phil, do you guys want to comment on additional comment on this in terms of
Yeah, that's correct. So you don't need to consider the cross cases like this, Jung, when you do optimization, meaning when you do place and route. So, but when you sign off, certainly you need to consider all combinations, mean fast, slow, fast, flow, and every combination. So, for example, if you have during optimization, you have 4 analysis views, for example, like a functional fast and functional slow, test fast, test low. So you optimize at those 4 corners, for example, but when you sign off, you will turn on 34 corners, 120 corners, depending on what you're running. So when you sign off, you have to have all kind of a combination, and once in a while you will see some weird violations in those kind of cross corners, and you would fix by an ECO, for example.
Yeah, so when in field was talking about sign off, which mean that there's you sign up on timing. There's a STA, which is static time analysis. They run thousands of corner cases to sign up all the timing on a various combination that we don't normally do in implementation, which is PD. Okay.
Yeah, very good questions. Thanks for the questions.
It seems like he suggesting the cross corner, is it? The slow timing library and then fast RC. Is that what you're talking about?
Yeah,
I
so
think
he's
so.
asking.
I think so. Yeah.
Yeah. Yes. Okay. So yeah, if you think other questions, just feel free to ask. Okay. We have a lot of time for questions today. So let's get back to post CTS op. Okay. So after you run CTS, right? CTS, part of it is building the trees. Now part of it is also fixture timing. But it doesn't guarantee that you're gonna have it's gonna be clean when you come out of CTS. So the step here we'll call post CTS. Post CTS meaning after CTS, after the tree's been built, right? So here's a chance you can do additional optimization trying to fix remaining timing violations, whether it's set or whole. Okay. So at this point, after you run CTS, you do one step of optimization post CTS. Your WNS and TNS. Remember what WNS and TNS is? WNS is your worst negative slack, and then TNS is total negative slack. And so basically the sum of WNS is going to be your total DNS. So you can take a look at here, right? So this is a summary of your timing your design timing. So this is WNS. So in this particular one here, you can see WNS is negative 185 0.185 nanosecond, 185 picosecond. So remember, negative slack is bad. That means you have violations. So if you look in different time groups here, your registry is clean. So this is where your memreg, this is where the violation is. Okay. So all the other timing groups are clean, except in this example, this is memories register grouping. So, okay, so there's 3 paths that violate. So these are number paths. There's 3 paths that violate, and the 82 paths. This is how you read it. Okay, and also the register mem also an issue here. Okay. So basically, I mean to say here is that there should be some minor violation, not major, not total slack should not be somewhere in the minus 15 or 20s. Okay, if you do at this point, you get some big issue, a timing challenge that you got to go fix. So where you have numbers like these, you can run a post-op CTS. So this is I know the command here that you're gonna run in the labs. Okay, so this is for setup. As far as whole, you can see in the whole we still have some violation here. 74 picosecond violation for the whole, and it's coming from the input, right? So the default is input. So total negative slack is 855. Okay, so likewise you can run. So in your design, in your lab, after CTS, if you have timing violation, you can execute, you can run a post op step to clean it up, and it usually clean it up. If it doesn't clean up, you can do an incremental post op, and it should bring you pretty close. So I noted here, so sometime you might need to run incremental after this if there's some timing challenges in the design. Okay, so you just add an incremental op, and it will run an additional step. So sometimes we do 2 or 3 passes to clean up on a design that has a timing challenge, meaning difficult to close. Okay, so this is what post-op is after CTS. Okay, so just keep in mind, after you're in CTS, doesn't mean that your timing will be automated clean. So if there's violation left, whether set or whole, you run accordingly. So you can run a post-op. If that's not clean, you run a second pass, op design incremental, and sometimes we actually run additional pass also to see if that clean up. If not, then you look at your detailed timing report to see, in whichever group that has violations. So you look at that detail and try to analyze that path by path. Or you bring up the timing debugs to see where the longest delay with sales. Okay, any questions on post CTS op and why we need to run it? And so this generally what all the tools, I mean, we use Innovus, Cadence, but Synopsys is the other tool. It also do the same thing. The syntax may be slightly different, but the steps are the same. You run CTS, and then after that you run post-op optimization, and you can also run incremental ops. So the concept is the same. the syntax may be slightly, it's gonna be different. Okay, it's gonna be different according to the tool, but the stepwise, the concept is the same across any tools. Okay. Any questions?
There's one.
Let me see here. Okay, can you ask WTNS, WNS and TNS should be smaller after CTS? How small? Okay, so it's relative. It depends on your design. So if your design is larger geometry where delays is in nanosecond, it's more a relative. So here in this design here, meaning that depends on, so here you only have total 19 paths. So maybe perhaps look at the number of paths is better than this relative number. So you should have a smaller number of violating paths. So could have 50 less than 100. You have 1,000 and 1,000. If you have 1,000, the number is going to be huge. Okay, so it really depends on the technology you're using. So here, it's 105 picosecond is this is 40, this is 4 this is 4.5 micron technology, I think. So for this technology, this is small, okay. But for a 3 nanometer, this is huge. So it's relative to the technology. But I guess better would be take a look at number of paths. If you have less than 100 or so, something manager 100, 200s. If you have 1,000, then you have huge issue somewhere. So it should be the number of total number of violating paths should be 100 or 200, less than 200, I would say. Okay, if you have
I want to add to that as well. So the purpose of TNS, right, total negative slack, and also the number of violating paths in this table. Let me see if I can annotate. See this one, number of violating paths. The purpose of them, TNS, right? This is what is a worst case violation on worst negative slack. But the total and the number of violating paths are there for the purpose of for you to see what is a magnitude. If you have in this case 12,000 paths, only 19 violations. So you say, hey, it is okay to accept certain violations here with the hope that the magnitude of violations is not very big, right? So that's the significance of total negative slack and violating paths. But if you have like 1 million paths and you have 200,000 violating paths, and you need to work harder during this stage, because the further you go from CTS to post CTS to route to post route, the further you go to the right, the harder to fix timing. So you want to do shift left, meaning the fixed timing violation as soon as possible. So by leaving this negative slack here, depending on the difficulty of or the degradation of the timing after you enter route and post route, it's based on your experience of what the nature of your design is. Some design and what the nature of all these violations is. So it's not like a rule of thumb here, but it's more of a methodology and understanding of your design, that you can make a determination whether or not you can live with negative 105 picosecond here, or you have to fix it all the way to 0, depending on how easy it is or how much it degrades after post CTS. Another mentioning is another thing to pay attention to is this number is really based on what you fit in as an RC and all the what is the status of your constraints and your parasitic during this post CTS. The more accurate it is to reality, the more accurate this number is. But if your setup is really not close to reality, then it can get a lot worse. So pay attention to also the RC models during this time, during post CTS. And if you see 105 here, but after you route and you see 500, then that means that your RC here might be too optimistic. So you do an RC tuning or RC calibration where you say for R, multiply by 1.1, for C, multiply by 1.2. So a process of calibration so that the timing that you have here reflect the reality when you have actual parasitics after routing. So those are different notes.
Yeah, thank you, Phil. I think you touched a little more advanced topic. We haven't talked about the RC calibration in terms of the rating factor and stuff like that. But anyway, that's something that you can do. Is more a little bit more advanced than this class. But thank you, Phil. Okay. All right. So any more questions about the post? So this is just, I mean, post CTS ops. This is really it. I don't have any additional slides to talk about because it's just, it's just optimization technique that the CTS tool uses that we talk about already. So basically, look at all the different timing slack, right? What's violated, what non-equal, and if focus on this, if this particular group is violated, when you run post up, it's going to focus on these violations on this timing group, and that's the high priority, not these other groups. Okay, so the incremental are usually going to run a lot faster than your full op. Okay, and make sure you give us a different prefix, right? You when you run it, the report prefix here I call CTS op, and then you run an incremental called CTS underscore incremental, so you know that the timing report is written with a different prefix, so you can tell difference between which step as versus which steps, so you can go back and look. Okay, so let's on the next one. So basically, I have slides called impact of CTS, right? These so this is the design before we run CTS, right? So this is what it looked like, right? This is what happened to design. You add a clock buffers inverter, right? To balance the clock skew, right? And then, so once I added those in, your density is going to increase. So guess what? The density increase, your congestion will go to increase, right? And then, so what happens? Some of the non-clock cell maybe get relocated to another area where it gives priority to the clock cells, right? And then there could be new timing and DRV violations also because of the clock trees that get added, right? So those are some of the things that in terms of physically could happen to your design. So if your design is already congested here, you go to CTS, it's going to make it more congestions. So you remember you want to check timing and congestion after every stage to make sure it's still under control. Because if you have congestions and you're not fixing it, you ignore it, guess what? You go to the next stage routing, it's going to get worse. So that's why it's important to not only take a look at your timing, but also take a look at your congestion at the end of each stage and make sure it's still in check. Because timing is important, but also congestion is important. Because if you can't route the design, you can't close it. Okay? Closing it means it's not clean. So when we say close timing, that means meet timing. Okay, same thing with when you get to route in the next lectures or so. We'll talk about routings, and when you close the routing, mean you have to route it where there's no shorts. Okay, so very important to understand the impact of each step and what happens in your design. And you want any issue you want to address in that stage. Right? In placement, we care about setup time. We need to close setup time at that stage, and then we go to clock tree. Well, we got setup, we got hold, so we want to close both of those, or at least you have a few minor violations left when we go to the next stage, because it'll get you can see that design will get more dense and more dense as you move down the flow, right? Before, right, just no route. Now after CTS, the clock nets are routed, right? And the next stage, you can have all the detailed signals get routed. Things get more compact, more packed, and more congested, and it's more difficult to move things around. The tool doesn't have much room to move things around, or doesn't have much choices. So closing timing to the end get much more difficult. Okay, so everybody understood why these are the impact to the designs after clock tree synthesis. Okay, so you understand why there's could be new timing or DRV violation occur? So anybody chime in? Tell me why there could be new timing or DRV violation after CTS. So let's say your design is clean before, right? Before CTS, after placement, your setup is clean, your DRV is clean, except the clock nets. But then you run CTS, then suddenly you have new setup timing violation or a new DRV max fan out, for example. Why is that? Go ahead and you can do answer verbally, or you can chime in on the chat. I'll give you a few minutes to think. Think about what got introduced, what got added during CTS. Anyone want to take a stab at it? Okay, so North House said because during building clock tree, buffer are added to the launch and capture path. Okay. Yes, in the record, that's correct, because before we have zero clock delay, right? The clocks are ideal. So now that was the setup time was based on that, but now you actually have the clock skew or the clock delay, which in turn have clock skew. And remember, the clock skew impact your setup timing, right? So that's correct, Northern. Thank you. And then Ngok said after setup, you have extra skew, and setup and hold will be worse. That's correct. Good. And more routing paths, so more violation. Nguyễn Duyên said Duyên. Okay. Yeah, so so all those contribute to why timing get worse or degrade in after CTS. Good.
So I want to add, on Ngô Quốc Thái, so all good guesses, by the way, Ngô Thanh Hào, Nguyễn Văn Duyên, Ngô Quốc Thái, but on the getting worse, it depends, right? So before the clock trees are inserted, the clock skews actually are modeled. So you have clock skews model, say 200 picoseconds. The skews, meaning that if you have different arrival times on different destinations, you want to model the actual variations, versus just zero skew, right? And then after the clock trees are built, some of the skews might be better, some of the skews might be worse. So it's not entirely accurate when we say setup and hold will be worse. It can be worse in certain paths, and generally it will be worse depending on how aggressive you set the skew, before CTS. But it can be better in some cases. So I just want to make sure we all understand the methodology here. It's not like before CTS, we don't have skew models. So the skews and latencies are modeled during synthesis and during pre-CTS to make sure that we anticipate all these different variations, so that we won't be too optimistic during pre-CTS. After the clock trees are inserted, then the actual delays are used and the skew models are ignored. So the timing enter a state where they call clocks are propagated. So the term propagated versus the term zero delays on the clocks with skews being modeled. So it's important to understand that. So before CTS, you actually need to model the skews and latency.
Yeah, so thank you. So let me link it back to some of the term we use in a couple lectures. So remember we talked about clock uncertainty. Remember we discussed that is used to model the clock jitter or the uncertainty on around the edge of the clock. That's the model of the skew that's Phil talking about. And then depending on the whether it's get worse or better, generally it get worse, but some path it will get faster, like he said. Remember we talk about positive and negative clock skew, how it impact. Remember the positive skew, what it does to set up versus what it does to how it back hole. We discussed that in believe lecture 14, maybe 15. Okay, so you guys should know the impact on the skew, what happened. It could speed up or slow down, how it impact the 7 hole. Okay, but generally things will get in general things will get worse. Okay, but on some specific path it can get better depending on setup of hole. Okay. Thank you for you guys' questions, and that gave us a seat to discuss more things about more topics and details versus also kind of remind us what happened, some of the topic we've learned. Okay, anything else before we the next slide I have is going to talk about CTS outputs, and then the how to qualify, what are things you're looking for CTS, how do we know CTS's results is acceptable. Okay, since no questions, I'll go on to the next slide.
But there was one additional question. Could you talk about why the new DRV violations occur?
Oh, okay. So why in a similar manner in terms of, because on the thing could get changed, right? Talk about where some of the cells may get relocated. So let's say on the signal DRV, I'm not talking about clock map, let's just address the signal DRVs, right? So before, some of those cells are fine, but it will get relocated because of the clock trees, right? It can move those cells, so it can move it further away. That means if it's on the edge of really on the edge of meeting the DRV rules on the let's say the max cap. So if the cell got moved up further away, then the net get longer, therefore there are more caps. So those can introduce new DRV, new max cap. Does that make sense? Okay. All right. Thanks, Noel. Time for your questions. Okay, so just like all the other stage we discussed here, I think you guys kind of figure out what would be the outputs, right? We discuss all these care about along the way, so you know that when at every stage we're gonna have to write out a net list, right? Optimized net list for that stage. When I say optimize, the term optimize means that it's already been optimized and timing been fixed to meet the target for this stage. So okay, so the optimized def, setup timing report, hold timing report. This is the first time that we care about the hold timing, right? After CTS, before CTS, we don't close the hold. So only the clock tree is in with skew, then we care about hold timing. And of course, we take a look at the clock reports, error clock reports. I think we already discussed, take a look at clock reports. If not, we'll look in the lab. And then skew reports, and of course, power reports. I didn't list it here in terms of the congestion. So those we always looked at, right? Congestion numbers, both the overflow and the hotspot. So we always look at those. Right. Okay, I thought there was a question pop up. Maybe not. Okay, so these are the outputs. Okay, pretty much you write out. I mean, by now you should know that we write out a DB, right? A DB. From the DB, you can write out net list and whatever SDC and whatever you need to is all contained in that DB, the database, and that will get read into the next stage. Okay, so this is the outputs. Any questions on the outputs? What's come out of CTS? I think the only thing that is here that new is the clocks related information, right? The clock report, skew report, hold time report. Those are the three things that I can think of that are new versus what was before out of placement. Okay, so this is pretty much self-explained. So let's go to. Okay, so let's review and go ahead.
Yeah. So yeah. But did we talk about the significance of the actual skew results in terms of time and closure? So meaning that when you see the results, the resulting skews, if it is not too small for your liking, you wanna optimize the skew, minimize the skew first before you go on and fix timing, right?
You're talking about the clock ECO? Will we fix the clock skew?
Yeah, talk about the methodology in terms of clock skew. So choosing a target and analyzing the quality of the skews is an important methodology step. Meaning that when you do a skew report, right? If you go back to the previous slides, right? When you do a skew report, you will want to pay attention. So the skew report is next to the last bullet, right? When you look at the skew report, either you take them as is, or you say, hey, this skew the word skews on this particular clock is more than what I like. Say if I put target of maximum skew 100 picoseconds, and the skew on this is 120. Before I go on and do the clock post CTS optimization, I want to see if I can improve that skew, regardless of what the timing is. So I want the student to understand that's part of the methodology, that sometimes you want to minimize the skew as much as you can first, because the more skew you have, the harder it is to fix timing, the more areas and power is needed for certain target speed. So do pay attention
we
to
talked
the,
about that.
right. Okay.
We did talk about that, and then in the lab there will be we will discuss the clock tree debugger and so on. Yeah. So we touch up on that until, but we didn't go into the details where if we have issue in terms of the clock series long, how do you go about fixing what method and so on. That I thought was too deep for this class.
Yeah, I just want to make sure we analyze and say if we want to improve on it before go on. It's just a methodology, right?
Yeah, so
Okay.
in the last lab, the student have a chance to analyze the clock tree using the clock tree debugger in the tool, and how to use that and analyze what's the longest path and bring that up, and then physically also cross probing to see where they are and if there's something can be improved.
Okay, thanks.
Okay. Anything else? So okay, so the as far as qualified CSS result, qualified timing is set up is similar to pretty much last stage. You make sure that it's clean, or there's only few minor paths that showed up. In this example here, for the lab I ran, it's clean. It's some of setup time. After I ran after post-CS op, you can see here there's 0 path violations, right? Everything is positive. So this is good. So this is the first time we take a look at the hole. So you also want to make sure the hole is also clean, or at least there's maybe 1 or 2 or on the hole. But hole are much easier to fix than set up. Okay, so it should be clean unless they're on a difficult design. There may be a path where it's not clean because it's straddle both setup and hole. What I mean is straddle mean also conflict path. I think that's easy to understand. Conflict path, meaning that if you fix hole, you're going to violate setup. If you fix up, you violate hole. Okay, so those are the paths that either way is conflict path. Those are much more difficult to fix. So those you may have to go and look at it manually, and the tool not be fixed. You may be able to fix by moving cells or the clock or something like that, similar. Okay, but it whole time should be clean except some of those difficult paths, those conflict paths. Okay, and all DRV should be clean. Okay, at this point, because remember in placement you have the clock trees. That was the exception because the clock tree has not been synthesized, hasn't been built. So here we already built clock trees, so your DRV should be clean. So you can notice here everything is clean before we have some violation because due to the clock nets. But here it should be clean. Okay. Any questions? Comments? Okay. So timing, DRV. Okay, so I always check placement. Okay, so make sure that all the placements should be clean. But here you can see this example, I purposely put it here you can see there are violations here. Okay, I flag this. There should be no violations. If there is, you need to take a look at it and fix it. Okay. So fix it. And remember, we do a incremental placement. Okay. So usually there's some reason why at this time there are violations. So it could be some fences that we put in, and then the cell got put inside of it, and that's why when we do a check, it's show up violations. So we might want to move it out of there. Okay, but this should be clean. I purposely put it here to show you a violation, but this should be clean. Okay, and make sure the design is still routable. All your congestion is still under control. So remember, in Innova's term, over less than 1%, it is most likely to be routable. Anything over that is a bit more challenging. Maybe the post, but it'd be a little bit challenging. Okay. Likewise with hotspot, this is pretty much the guidance from Cadence. Okay, and I've been obeying this for a while, and that got me through even large design with millions of instances. Okay. Okay, so this is pretty much similar to placement in terms of checks. Okay, power requirements, similar. So you want to do report power, okay, and make sure that they still meet your target. Okay, here's a new one, clock skew, okay. So you might want to make sure that your clock skew and your clock insertion delay meet your target, okay. So this is the clock skew report and insertion delay. So you can see here, this is a test chip for the lab. You can see different corners here, and you can see is the target here I set for this clock, this the main clock and the test clock. The ID is 1 nanosecond, 800 picosecond, right? The rest, okay, so I set it here. You can see it's an ID target. So, and also this, I set the skew target. You can see this 800, right? And it reported here, this is the min insertion delay and max insertion delay. Okay, so minute is the shortest path. Remember we talked about when we have those different clock branches, right? You can have shorter, longer one, trying to balance those. If it balance the timing arrive at the same time, then your skew is going to be minimal or 0. Okay, so this is the min meaning shortest path, max meaning the longest path. Okay, and this is average. Okay, and this just report the deviation between min max. And this is the skew target type. So it's explicit here, meaning that the user set it. So this one is being set, right? So explicit meaning we set it. So skew target is 800, and you can see that the skew target here is, it can actually beat it. So I just put something down here just to see the on this design. Okay, so you should know what the target is and set it. So here the skew is all in the 300s, except these other one, right? So the Windows occupancy, here. So I highlight the average ID. ID is stand for insertion delay, and then the skew. So these are the numbers here that you want to make sure that it meets your targets. Okay. And Phil was alluding earlier, if you get some skew that you don't like or longer than you expected so you set it, you say your target's 300 and something at 500, you may want to go back and look at it, see why that tree, pull up your clock tree debugger and see why that particular clock is at 500 versus others at 300. Maybe it's too many things, or the sync is spread out, placed far away from the source, and then clustered together, or something like that. Okay, so you want to look at that if that's something out of your range.
So to add the practicality or the real world experience to this, so if you were working on your last 3 nanometer design with MediaTek, but when you look at the SKUs like this, what would you do? Like is a 300 range above 100 range? Would you do something about it, or you just go on?
It depends on the requirements, right? If the requirements, so for example, yeah, it depends on the requirements of each of the clocks. Okay, so if our target is 200s, then yeah, I would go look at look and see, trying to bring it down, or even a target 250. So we have to go looking down. Yeah. So anytime we miss a target,
what would be a good target for your past design at 3 nanometer?
the clock skew.
Yeah.
At 70 picosecond.
Yeah. So just to add to it, right? So 300 here. Yeah. So you have like 370 picoseconds. Usually depends on the technology and your target speed, but 300 is way too slow. So yeah, that's why depending on your design, if it is even at 22 nanometer, is 300 here is way too much of a skew. So you do want to take a look, and you would try to do a CTS with a target skew at 0 first and see what the best it gets. And then look at the so it will try its best to minimize to the best it can at the expense of latency. And then if you have smaller skews than 300, and then you have reasonable latency, then you say that is what I want. But if the latency is too long, then you want to consider relaxing the skew. And it's advanced topics, but I want to make sure you're aware of those latency and skew relationship and things that you should pay attention to be a good PD designer. Actually, it's high at 10 o'clock now. Is that a good stop for the scholarship announcement? But
Sure. Yeah, that's I have yeah, the next few slides summary, so I can go over those and then go over the lab. So this is your time. Sure. Yeah. Okay, so I'll go ahead and stop here, and we'll pick it up after the scholarship announcement, and then a little break after that. Okay, go ahead. Wang or Phil.
Okay, so như Định trình bày thì những cái chi tiết về một cái chương trình với lại một đại học bên Đài Loan đã được chia sẻ, và hôm nay có sự tham dự của anh Nguyễn Khánh Linh từ Trung tâm Đổi mới sáng tạo, và có thể không biết Quang có ở đây không? Quang Nguyễn Vinh Quang là CEO của FSemi. Đây là hai người quan trọng trong trong cái ban tổ chức chương trình học hôm nay. Thì xin mời anh Nguyễn Khánh Linh có thể trình bày về cái chương trình này ạ.
Vâng, cảm ơn chú Phiêu ạ. Chào tất cả các bạn sinh viên, chào tất cả các thầy cô. Thì cũng cảm ơn chú Phiêu và các thầy cô đã đồng hành cùng chương trình trong thời gian qua, cũng như là cảm ơn các bạn sinh viên đã tham dự ra cái khóa đào tạo của NIC. Thì chương trình này thì là ấp ủ của Tresemme, FPT và NIC để mà là gọi là cái khóa đầu tiên về đào tạo ngắn hạn. Sau này sẽ còn những cái khóa khác mà liên quan chuyên môn sâu nữa, thì sẽ là hy vọng sẽ nhận được sự tham gia của các bạn sinh viên xuất sắc ở đây. Thì thì NIC thì là như các bạn cũng đã biết là là cơ quan được Thủ tướng Chính phủ giao cho xây dựng đề án phát triển nguồn nhân lực ngành công nghiệp bán dẫn. Vì thế thì trong thời gian qua thì là NIC cũng đã làm việc với các chuyên gia như là TSMI, rồi các tổ chức quốc tế, các doanh nghiệp lớn ở trong và ngoài nước, để mà xây dựng cái đề án phát triển nguồn nhân lực mà 50.000 kỹ sư mà các bạn hay nghe đấy, là NIC là người chắp bút đấy, thì là đang chờ thủ tướng, đã trình thủ tướng ngày 27 tháng 3 vừa rồi, và đang đang chờ thủ tướng thông qua. Tinh thần là sẽ đặt mục tiêu là đào tạo 50.000 kỹ sư. Thì trong lúc chờ thủ tướng phê duyệt cái đề án đấy, thì là NIC cũng đã có một số những cái chương trình để mà hỗ trợ liên quan đến đào tạo nguồn nhân lực trong phát triển ngành công nghiệp bán dẫn, như là chương trình này, chương trình học bổng về Tresemme này, hoặc là có những chương trình như chẳng hạn như là một số bạn ở đây là đã được học những cái các cái tool liên quan đến Cadence mà ở trường ấy, chẳng hạn như là các trường đã triển khai như là Đại học Bách Khoa, rồi Đại học Quốc gia, là đã cài và sử dụng được cái phần mềm Cadence ở đấy. Thì đấy là những cái mà NIC cũng đã triển khai. Rồi thì sắp tới sẽ có những cái tool khác, như như là sẽ đưa vào đào tạo ngắn hạn như là Siemens EDA. Siemens EDA thì trước là Mentor Graphics đấy, thì sau này cũng sẽ có đưa vào cho các trường để mà hỗ trợ các bạn để mà được sử dụng các cái tool của các công cụ thiết kế chip từ các doanh nghiệp hàng đầu thế giới. Để chia sẻ với các bạn là một chút về cái định hướng phát triển nguồn nhân lực ngành công nghiệp bán dẫn của Việt Nam, để các bạn là những người trực tiếp tham gia vào cái ngành công nghiệp này để các bạn hiểu hơn. Thì là Việt Nam là có chia ra làm 3 giai đoạn. Từ giờ đến 2045 là chia ra làm 3 giai đoạn liên quan đến ngành công nghiệp bán dẫn. Giai đoạn thứ nhất là trước 2030, giai đoạn thứ hai là 2030 đến 2040, và giai đoạn thứ ba là sau 2040. Thì trước 2030 ấy, là bởi vì là ngành công nghiệp bán dẫn, tuy là Việt Nam có ngành công nghiệp điện tử rất là phát triển rồi, với các ông lớn như Samsung, các cái hệ sinh thái rất là hoàn chỉnh rồi, nhưng mà cái ngành công nghiệp bán dẫn của mình vẫn là khá là non trẻ. Có nghĩa là ở đây các bạn cũng biết là các cái lĩnh vực đóng gói thì mình có Intel, rồi cũng Amkor, Hana Micron cũng vừa mới vào. Rồi thì mình có khoảng 40 doanh nghiệp về thiết kế chip đấy. Rồi, nhưng mà về các pháp thì mình cũng chưa có. Tóm lại là cái mình là vẫn đang khá sơ khai về ngành công nghiệp bán dẫn. Thành ra là trước 2030 sẽ là Việt Nam sẽ tập trung vào câu chuyện là phát triển nguồn nhân lực đấy, để mà chuẩn bị để mà sẵn sàng cho cái chuẩn bị không chỉ nguồn nhân lực mà còn là về hạ tầng điện nước, rồi chuẩn bị về cơ chế chính sách để mà sau 2030 là sẽ là thứ nhất là có các cái fab, các cái nhà máy sản xuất chip họ sẽ vào Việt Nam đấy. Rồi cũng như là câu chuyện là hiện tại là chẳng hạn như lĩnh vực thiết kế chip là hiện tại là đa số các doanh nghiệp ở đây là toàn là doanh nghiệp FDI, rồi doanh nghiệp làm về có một số doanh nghiệp Việt Nam nhưng đa số làm về outsource đấy, có nghĩa là mình bản chất là đi làm thuê đấy. Mình định hướng sau 2030 sẽ là sẽ có một số doanh nghiệp Việt Nam trong lĩnh vực thiết kế chip là làm chủ các IP, làm chủ công nghệ đấy, có nghĩa là tự phát triển chip luôn đấy, chứ không chỉ là dừng ở bước là outsource như bây giờ đấy. Thành ra là trước 2030 thì chính các bạn là thế hệ mà chuẩn bị để mà cho cái mục tiêu rất là lớn sau 2030 đấy. Thì bên cạnh những cái chương trình mà NIC đã làm đấy, thì có những cái chương trình mà NIC cũng đang làm việc với các đối tác để mà trao học bổng cho các bạn đi học ở nước ngoài đấy. Mình học tập cái mô hình như là ông Nhật Bản cách đây 40 năm, ông Đài Loan cách đây 30 năm, ông Hàn cách đây 20 năm, là họ cử người đi nước ngoài để mà đào tạo. Như mô hình TSMC là cũng ông Maurice Chang là ông Maurice Chang cũng 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 đã là học tập ở Mỹ, cũng như là làm việc ở Texas Instruments, rồi sau đấy về mở ra TSMC đấy. Nói chung là các cái doanh nghiệp lớn về bán dẫn hiện tại là đa số đều là từ các nước như là Nhật Bản, Hàn Quốc hay là Đài Loan các thứ, thì đều là từ các du học sinh trở về. Thành ra là là NIC cũng đang phối hợp với một số bên. Thì trong đấy thì là có cái chương trình là phối hợp với trường đại học Dương Minh Giao thông của Đài Loan, là top 2. Một số lĩnh vực của họ vẫn là top 1 đấy. Về lĩnh vực bán dẫn thì họ là nằm ở ngay khu công nghệ cao Tân Trúc. Thì Tân Trúc là nơi mà đặt tất cả những cái tinh hoa nhất về bán dẫn của Đài Loan, là từ TSMC, tập đoàn TSMC, UMC, MediaTek, hay là các tập đoàn sản xuất bán dẫn. Rồi thì những cái thiết kế chip thì họ cũng đặt ở đây bởi vì phục vụ cho các hệ sinh thái, thì các nhà nhà máy ở đấy, thì thành ra các công ty thiết kế chip họ cũng đặt ở đấy. Rồi thì các cái viện lớn như là ITRI rồi TSI các thứ là người ta đều đặt ở khu này hết. Thành ra là NYCU thì một thông tin để các bạn hình dung là 2/3 các CEO của các doanh nghiệp, của hàng nghìn doanh nghiệp ở khu công nghiệp này ấy, là người của NYCU, là cái Đại học Dương minh Giao thông rồi đấy, để các bạn hiểu là cái trường này nó tinh hoa như thế nào. Thì ví dụ như là họ chẳng hạn phía Hoa Kỳ thì họ cũng hợp tác với trường Đại học Purdue chẳng hạn, thì là cũng là tinh hoa của Hoa Kỳ đấy. Thì đặc thù ở có nhiều cái ngành trên thế giới ấy, thì ở Hoa Kỳ lại là tinh hoa, nhưng mà đặc biệt là trong lĩnh vực sản xuất cũng như là bán dẫn này, thì ông Đài Loan lại là ông số 1. Bởi vì sao số 1? Bởi vì là chẳng hạn như là TSMC người ta mở cái nhà máy ở Mỹ, thì là chẳng hạn như là kỹ sư Đài Loan người ta không sang Mỹ người ta làm đâu, bởi vì là người ta lương ở Đài Loan người ta vốn dĩ đã cao rồi, người ta không việc gì người ta phải đi hết, về cái công nghệ ở Đài Loan đang tốt hơn ở Hoa Kỳ nữa đấy. Thành ra là họ ưu tiên làm việc ở kỹ sư Đài Loan, người ta ưu tiên làm việc Đài Loan hơn. Thành ra chẳng hạn như những cái nhà máy ở ở Mỹ chẳng hạn, thì bây giờ đã lại cái kỹ sư Mỹ phải làm sang Đài Loan để mà học về bán dẫn, hoặc là ở công ty đấy là phải đưa kỹ sư Đài Loan sang các cái mission, sang cái đào tạo ngắn hạn cho các kỹ sư Mỹ ở bên kia một thời gian để mà họ làm chủ được cái dây chuyền của công nghệ, rồi sau đấy kỹ sư Đài Loan lại back về Đài Loan đấy, để các bạn hình dung là đặc biệt trong cái ngành này thì Đài Loan là mạnh như thế nào. Thì NYCU là top đầu rồi, thì họ ở đây thì họ đã làm việc với Việt Nam để lần này cũng cung cấp một số học bổng thạc sĩ, là nhất là rất là phù hợp với các bạn sinh viên năm cuối, thì các bạn rất là đa dạng từ thiết kế chip cho đến vật liệu cho đến sản xuất. Thì chương trình này là được đặc thù là đào tạo hoàn toàn bằng tiếng Anh đấy. Thì họ đây là giảng viên là không chỉ là người ở Đài Loan đâu, họ sẽ là có đợt trước mình sang thì là giảng viên là còn có nước ngoài nữa, ở Mỹ, ở Anh, ở Pháp, nói chung là rất là đa dạng. Chương trình hoàn toàn bằng tiếng Anh. Thì là cái chương trình này là được thực hiện tại Học viện Bán dẫn của Đại học Dương minh Giao thông. Học viện bán dẫn này là cái mô hình đào tạo, có nghĩa là dựa trên nhu cầu doanh nghiệp, có nghĩa là doanh nghiệp người ta đặt hàng trường, có nghĩa là trường không phải là các bạn học xong mà các bạn bắt đầu đi tìm việc đâu. Các trường này có nghĩa là ờ, các cái doanh nghiệp người ta đến đây, người ta là đưa cho trường đấy, đây là danh sách các skill mà tôi muốn nhân sự của tôi có được đấy. Thì trường sẽ đưa vào cái giáo trình để mà đào tạo cả liên quan đến lý thuyết ở trường các thứ, một thực hành ngay trực tiếp ở doanh nghiệp luôn. Nên thực ra kỹ sư này là thế hệ kỹ sư thực hành rất là xuất sắc. Thành ra là rất là hay. Thì là các bạn sẽ là nếu về cái nội dung này thì đợt trước thì là mình cũng đã gửi thông tin cho phía trường, là giới thiệu là NIC cũng đang phối hợp với FPT và Dasemi có cái chương trình học bổng ngắn hạn về thiết kế chip. Thì họ cũng rất là thích chương trình này. Thì mình cũng đã gửi cái danh sách các bạn ở đây, bao gồm tất cả các bạn ở Hà Nội, Đà Nẵng, Thành phố Hồ Chí Minh. Thì thì họ cũng đã xem qua, và họ cũng đánh giá cao cái danh sách này. Thì thứ hai tới đây thì ông viện trưởng của cái viện bán dẫn đấy thì họ sẽ sang đây, thì họ sẽ là có một buổi chia sẻ thông tin về học bổng đấy. Thì cũng như là tổ chức cái chương trình là họ sẽ là phỏng vấn trực tiếp đấy. Thì coi như là hồ sơ các bạn thì thông tin cơ bản các bạn thì mình đã gửi cho họ rồi. Thì có những bạn nào chẳng hạn quan tâm đến phỏng vấn thì có thể là ờ, tập hợp thông tin lại. Thì đến hôm đấy là chỉ việc đến phỏng vấn với các giáo sư của trường thôi đấy. Là tới đấy thì họ sẽ các bạn quan tâm thì đến đấy thì họ sẽ chia sẻ thông tin về học bổng, rồi cũng như là phỏng vấn trực tiếp. Thì về cái học bổng này thì các bạn sẽ là được 2 năm ở học bổng là 2 năm ở Đài Loan. Sau đấy thì các bạn sẽ làm 2 năm ở trong doanh nghiệp Đài Loan. Doanh nghiệp Đài Loan có thể ở Đài Loan hoặc có thể ở bất cứ đâu ở ở trên thế giới. Có thể là chẳng hạn như là doanh nghiệp này mà họ ở ở Hoa Kỳ hoặc ở Việt Nam thì là vẫn là có thể là các bạn vẫn đi làm cho doanh nghiệp đấy được. Đấy, thành ra là rất là nhiều cơ hội việc làm. Thì có một thông tin đấy là phía trường lại chia sẻ là lương của kỹ sư của trường này trong lĩnh vực bán dẫn ấy, là 100.000 đô. Không biết là mình có bị nhầm lẫn không, nhưng mà chắc là cũng cũng phải là sau vài năm đấy, mình đoán là cũng phải sau vài năm, nhưng mà lương chứng tỏ là lương cũng rất là cao ở Đài Loan, mà với mức sống nó tương đương với Việt Nam, mà lương trong lĩnh vực bán dẫn cũng cũng rất là cao, là khoảng 100.000 đô. Đấy là thông tin phía trước cung cấp, có cái file thì mình sẽ lát nữa sẽ gửi thêm cho các bạn. Đấy thì các bạn đấy thì mình chia sẻ một số thông tin như thế. Thì thì các bạn đây mình sẽ chia sẻ các bạn thêm cái agenda của cái buổi hôm đấy. Thì các bạn đã thấy chưa? Thì đấy thế sẽ diễn ra ngày sáng thứ hai ngày 15 tháng 4 ở NIC, chỗ Tôn Thất Thuyết, Cầu Giấy, Hà Nội. Chỗ các bạn ở Hà Nội thì đã ở đây rồi. Đấy thì mình chia sẻ trước cái chương trình Hà Nội trước. Thì ở Hà Nội là ngày 15 tháng 4, thì đấy thì chương trình buổi sáng thì sẽ là có ờ, đến 9:45 là người ta giới thiệu về trường một chút, sau đấy người ta sẽ tiến hành phỏng vấn theo là 4 nhóm, mỗi nhóm khoảng 15 bạn sinh viên. Thì là lát nữa mình sẽ gửi link đăng ký để các bạn cũng cũng đăng ký thêm. Đấy thì hiện tại thì cũng là ưu tiên các bạn thôi, vì các bạn đây là cũng đa số là từ các trường xuất sắc ở Việt Nam rồi, cũng như là các bạn là cũng đã trải qua những vòng hồ sơ cũng như vòng phỏng vấn từ NIC, vùng Tresemme và FPT, thì các bạn cũng đã là tham dự cái khóa này thì cũng đã được nâng cấp skill cũng khá khá rồi, đấy rất là phù hợp. Thì đấy là các bạn ở Hà Nội. Còn các bạn ở Thành phố Hồ Chí Minh thì là hiện tại là đang đầu mối, thì là chỗ Đại học Quốc gia Thành phố Hồ Chí Minh, là chỗ ban hợp tác phát triển, thì hay là chỗ thầy Huỳnh Phú Minh Cường cũng là đầu mối của cái chương trình của ngày 17 tháng 4. Thì họ sẽ là cũng mong muốn là lúc đầu là người ta định làm ngày 18 tháng 4, nhưng mà lại rơi vào đúng ờ, cái 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 lễ giỗ tổ, thành ra là họ sẽ làm vào chiều tối ngày 17 tháng 4. Thì cái đấy thì các thầy các cô của Đại học Quốc gia Thành phố Hồ Chí Minh sẽ trao đổi trực tiếp với các bạn, hay là nếu các bạn mà cần có thông tin gì thêm thì có thể hỏi NIC về chương trình đấy. Còn đấy các bạn Đà Nẵng thì rất tiếc là lần này bên đại học Dương Minh Giao thông sang thì họ cũng lại chưa 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 ghé Đà Nẵng đợt này. Nhưng mà các bạn gửi thông tin, những bạn nào quan tâm thì có thể gửi email cho NIC, cho TSME và FPT để mà bên mình tổng hợp, thì sẽ sắp xếp những cái buổi chẳng hạn như phỏng vấn online các bạn, để mà các bạn mặc dù ở xa nhưng vẫn vẫn có thể là tham dự. Hay ngay cả các bạn mà ở Hà Nội, nói chung là ở Hà Nội thì nên ưu tiên là tham gia phỏng vấn trực tiếp ở đây. Thì thứ nhất là để thông tin cho cụ thể, thứ hai là để phỏng vấn trực tiếp thì nó lúc nào nó cũng có những cái lợi thế nhất định. Những bạn nào mà khó khăn hay là mà không sắp xếp được, hay những bạn ở Thành phố Hồ Chí Minh cũng thế mà không sắp xếp được, thì các bạn email cho NIC thông qua cái email mà đợt trước đăng ký tuyển sinh vào lớp này đấy. Các bạn email về đấy thì bên mình sẽ làm việc ở phía trường để sắp xếp những cái khung thời gian phỏng vấn cho các bạn. Đấy thì vừa rồi thì mình có chia sẻ cái chương trình học bổng ở Đại học Giao thông Giao thông, thì cũng là như mình trao đổi cũng đang ưu tiên cho các bạn để tham gia chương trình đào tạo ngắn hạn của mình ở đây. Mình cũng biết là có nhiều bạn ở đây là cũng đã apply vào chương trình học bổng với Samsung chẳng hạn. Samsung thì họ đang triển khai ở với Đại học Quốc gia Hà Nội, là cái chương trình 40 bạn sinh viên mà học tại Việt Nam, sau đấy làm với Samsung. Thì cái đấy cũng là một chương trình hay, mà nếu các bạn nào cân nhắc nếu mà đi học ở nước ngoài cũng là một cái trải nghiệm thú vị. Đấy, bản thân mình cũng ở nước ngoài cũng hơn 10 năm rồi mới về Việt Nam, thì cũng là một trải nghiệm rất thú vị. Thì đấy thì mình vừa chia sẻ thông tin về cái chương trình học bổng, cũng như là để các bạn quan tâm tham dự. Đấy thì không biết là các bạn ở đây thì có bạn nào có câu hỏi gì cho NIC không? Các bạn cứ tự nhiên nhé.
Linh ơi, có một cái câu hỏi trên chat bảo là nếu mà học sinh viên ở Hồ Chí Minh á, thì phỏng vấn online ha?
Vâng, sinh viên ở thành phố Hồ Chí Minh thì có hai option. Thì bởi vì là đoàn của NYCU thì họ sẽ là có sắp xếp phỏng vấn vào chiều tối ngày 17 tháng 4 thì phía trường là sẽ trao đổi. Đấy. Còn lại thì vẫn là có thể sắp xếp được online. Đấy, nên các bạn cũng cân nhắc thì nếu gặp gặp trao đổi với các giáo sư của trường vào chiều tối ngày 17 tháng 4 thì sẽ là rất là tốt. Đấy, nhưng mà trong trường hợp các bạn không không dự được thì có thể là bên mình sẽ kết nối với phía trường online để mà cung cấp thông tin thêm.
Vâng, Nguyễn Văn Long ơi, cứ cứ bật mic lên rồi hỏi trực tiếp luôn nha Nguyễn Văn Long.
Có một bạn hỏi về cái CV thì các bạn cứ 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 mang theo cũng được, nhưng mà tinh thần thì bên mình đã gửi cho bên trường thông tin cơ bản rồi đấy, nhưng mà tôi cứ mang theo đi cho chắc cũng được. In cái CV ra, nhưng mà tinh thần thì về thông tin các bạn như GPA, điểm tiếng Anh các thứ thì đã bên trường đã có hết rồi đấy. Ừ. Nói chung là cùng bên mình cũng ưu tiên các bạn tham dự chương trình này, thành ra là cũng sẽ là được cụ thể hơn là các bạn mà đăng ký ngoài. Các bạn cứ đặt câu
Vâng.
hỏi nhé.
Ừ. Yeah. Còn cái email là sẽ là email mà mấy bạn ghi danh phải không Linh? Hình như
Dạ vâng,
nic@, thì
vâng.
lát nữa
Dạ,
sẽ copy đưa lại thêm, thì cái đó sẽ đi đến thẳng Nguyễn Khánh Linh thì có thể trả lời
vâng.
thẳng được. Và trong khi chờ đợi những câu hỏi thì tham dự hôm nay cũng có Nguyễn Vinh Quang là sáng lập viên và cũng chủ tịch hội đồng điều hành CEO của FSME. Vì Quang lần đầu thì định phát biểu nhưng mà vì đang di chuyển thành thì không tiện nói, nhưng mà đang tham gia. Cảm ơn anh Quang đã tham gia. Mọi người muốn hỏi gì tiếp thì cứ bật mic lên hỏi trực tiếp. Ok, đây là một cơ hội rất là lớn cho những học viên của cái lớp học hôm nay. Thay mặt Trasemi thì chúng tôi cũng rất cảm ơn NIC đã có nhà ý cho những ưu tiên cho những học viên của lớp này, và cũng cảm ơn sự hỗ trợ của FPT và những đối tác khác. Thì hy vọng là học viên sẽ lợi dụng cái ưu ưu tiên này để mà có thể là xin những cái học bổng thì nó chưa rõ, nhưng mà những cái chương trình học thạc sĩ này và có những học bổng trong năm đầu cũng như năm thứ nhì mà các chi tiết đã có nằm ở trong những cái file mà đã chia sẻ rồi. Thì hy vọng sẽ có một số người xuất sắc trong này lợi dụng cái ưu tiên này mà để nhận học bổng và đi du học. Đấy, cảm ơn Linh đã bỏ thời giờ mà anh Linh đã bỏ thời giờ mà chia sẻ những cái thông tin này hôm nay.
Dạ, cảm ơn chủ phiêu ạ, cảm ơn các bạn sinh viên, cảm ơn các thầy cô đã lắng nghe. Và
Ok,
Ok,
nếu
vậy
không có gì ai nói tiếp đi. Vâng.
anh Phiêu nói rồi anh Phiêu.
Không anh Phil không có nói gì định nói, nếu mà không có câu hỏi gì thì sẽ rồi có thể có câu hỏi thì sẽ hỏi thêm, nhưng mà Bạch nói đi Bạch.
Không thì ý đó là nếu mà mình thì xong hết thì mình quay lại cái chương trình của mình. Vậy thì mình cũng còn một ít thời gian thôi. Ok,
Phỏng vấn này là cho vị trí PD thôi anh Linh có câu hỏi như vậy.
dạ, chào nghe đấy chú. Vâng.
Thì có câu hỏi của Nguyễn Lê Minh nói là phỏng vấn này là cho vị trí PD Physical Design thôi phải không?
Như lúc đầu mình có chia sẻ thì chương trình này là khá là đa dạng, bởi vì là cái ngành bán dẫn của Đài Loan ấy, nói chung ấy, Nó sẽ bao gồm nhiều công đoạn. Thì trường này đặc thù của họ là từ câu chuyện là thiết kế cho đến sản xuất wafer rồi đến điện tử, nói chung là tất cả những thứ mà liên quan đến bán dẫn. Thì để mình chia sẻ cái nhóm lĩnh vực cho một chút để mình tải, mình chia sẻ cái file những cái nhóm ngành nghề.
Ok, vậy mọi người có câu hỏi gì tiếp thì sẽ đưa cái email để có gì tiếp hỏi thêm. Cảm ơn Nguyễn Khánh Linh và cảm ơn Nguyễn Vinh Quang đã tham gia và chia sẻ. Chắc bây giờ Linh đang ok. Ủa?
Ok, vậy Linh xong chưa Linh, hay là còn muốn thông báo gì nữa không?
Hình như Linh bị đây.
Linh ơi, unmute. Linh đang mute, không nghe được.
Chú đã thấy chưa ạ?
Rồi nghe.
Thấy rồi, nhưng mà hồi nãy mute không biết nên Linh có nói gì không?
Vâng, đây là danh sách những cái nhóm ngành nghề và công nghệ mà đợt tới sẽ liên quan đến chương trình đào tạo của họ, đúng không ạ?
Vâng, thì nói chung là không phải chỉ là NIC thôi, không phải chỉ là PD thôi, Nguyễn Lê Minh ạ. Là chương trình này, chương
Vâng,
trình về thiết kế bán dẫn và nhiều lĩnh vực khác nhau nữa, sản xuất cũng
dạ,
có. Vâng.
vâng.
Ok,
Thế thì
thôi cảm ơn Linh rất nhiều. Dạ vâng.
dạ, cảm ơn chú, cảm ơn tất cả mọi người ạ. Dạ.
Vâng, ok.
Ok, cảm ơn.
Thế trả lại cho Bạch.
Ok, thì xong hết rồi, cảm ơn mọi người. Thì bây giờ mình quay lại cái back to our lecture. Okay, everybody just switch gear back to CTS, okay? Okay, can everyone see my screen?
Yes.
Okay, thank you, Dave. Okay, so we got how much time left? We got about 34 minutes left, so I think we do. Okay, so back to CTS. So we were talking about reviewing qualified CTS results. So to summarize, basically no or minor setup time evaluation, no minor full-time evaluation. DOE should be clean. All cells should be placed, and congestion should be under control. And of course, power needs to be also met. And then your clock tree insertion delay and clock skew, make sure that it's within your spec. Okay, if it's not within your spec, then you need to go back and iterate on it to make sure it meets before you go on. Okay, so I'm going to move pretty fast here, trying to make up the time, but feel free to stop me, okay, if you have questions. Okay, so this just I put together a bullet here regarding CTS summary. Okay, so CTS step. Remember, there's 4 things happening in CTS step: clustering, balancing, routing clock tree, and post conditioning. Right, post conditioning is basically fixing minor setup and hold. Okay, and the next slide is key takeaway for CTS step. Okay, so primary goal CTS is to minimize clock tree, minimize clock skew, minimize clock insertion delay. Okay, so here a bad clock tree could lead to a poor design performance, poor power, poor area, and I think we went over those already. The reason why it could lead to poor performance, poor power, and poor area. Okay. And recall there's 2 types of clock skew, global and local skew, right? And you recall the global skew could also could impact system performance, overall design performance. Okay, and there are two type of clock insertion delay: source clock insertion delay and network. Okay, so networks clock insertion delay is the mainly one that we deal with, right? Well, it's from your clock source to your sink. Okay, we also went over different type of clock trees. We discussed 5 different types: conventional single source, clock mesh, H tree, fishbone, and multi-source. And remember, by default, most of the tools gonna do the conventional single source. Okay, so you look back your slide, you can tell what those are. Okay, we also discussed NDR rules, and in the NDR rules, basically that's central non-default rules, and in there you can specify the wider width, wider spacing, and also whether you want to shield or not with power and ground. Those are inside the NDR rules. Okay, we also discussed CTS exception, right? There's different stop pin, non-stop pin, through pins, floating pins, exclude pins, ignore pin. We went over the definition of those, and you need to understand those so that you can drive the CTS tools and instruct it what needs to be done so you can achieve a better clock tree. We also discussed the SKU groups and why we do them. Okay, so basically all the clocks within the SKU group are synchronous to each other, right? They come from the same clock source. And then each groups are largely mutually exclusive with one another, basically meaning they have no relationship. Okay. We discussed clock skew, positive clock skew. Remember what it can do, right? Positive, it helped the setup time, and it's hurt hold time. So that's positive clock skews when actually the capture clock arrive after the launch clock. That's called a positive clock skew. Opposite, you have a negative clock skew. It can help hold time, but it hurts setup time. That is when the launch clock arrives later than a capture clock. This is where you have a negative clock skew. Okay, so we spoke about this several times. Okay, we also discussed useful skews, right? It can be used to fix setup and hold time violations. In the last lecture, we discussed how we can use it. Okay, we also discussed duty cycle and how it impacts timing and minimum pulse width, and why minimum pulse width was important, right? And we also discussed the different type of clock tree balancing techniques, right? Cell relocations, level adjustment, reconfigurations, dummy load insertions, load splitting. Okay, so those are the things that the key takeaway that we discussed in CTS. Okay, any questions? This is really pretty much the end of the fundamentals for clock trees. Before we, I want to stop and pause here, see if you have any questions before we go, hit the labs instructions. Okay. Any questions or comments? Any additional comments from my colleagues? Or questions from students? Yeah, we also discussed single cycle path versus half cycle path, right? And you should know what those are. I know. Okay, if not, let's go on to the labs. So let me get out of here. Okay, so you should see the lab in the lecture material. This is lab 8. So this is the lab data. So same thing, the data it still look the same. The DB, which is from the last lab, pre-CTS that, okay, and the rest is the libs and the scripts are the same. The render contain the new run CTS underscore tickle 2.tickle, okay. So lab instructions here pretty much the same. Copy it over and you launch Innovus in the same format, okay. So this just show the script for this lab. Okay, so you can look at that later, but let me go to the detail step. So let's source you see under the render. So that's where I'm at. I'm go ahead and source run CTS2. So what this does. So this pretty much source this ticker script here. So it's just reading the pre-CS database and it'll stop. So the CTS database, remember, it has all the constraints already. When we read in the MMC file, it has the timing SDC constraints in there, has the clock definitions and so on. So it knows. So here the next step, we generate clock tree spec. So to generate clock tree spec, we execute a command called create clock tree spec and give it a file name called alpha. I call it ccop.spec. So go ahead and create it. So basically this will create a clock tree spec based on the SDC file that we have and some of the setting that we already been done. So let's go ahead and execute it. Okay, so you can see it ran. So let's take a look at the clock tree spec. So generally this serves as a base clock spec for design, and we'll go ahead and modify it or as needed, or you can use a ticker script. We went over this, I believe, some time ago in one of our lectures, showing you the SKU groups and different things that it actually had the clock definition and some of the stop pins. You can see here, it knows about the clock source right here, right? Group, the sync point, automatic, and then the yeah. So here's the clock definition for the. Oh, here's the. Remember we talked about general clock tree. We have a general clock tree here. It's called division clock, right? And then the source, and then it's generated by this clock, and the clock period is 8. Okay, so. Okay, so the parent clocks is it what is parent clock? Here. Yeah, name division clock source generated by this. Okay, so this is the main source. Okay, so down here, it knows about this. So since we have before we have the various clock, so it's created the different groups for us already here. If you know about the spec and this is not what you want, you can all go and alter it, change it, define it differently. Okay. So it know about automatic things and so on that we discussed, right? So it has this the basic one. So in the lab, I had you guy go ahead and just source this for default, and then we use Tickle to modify. Usually, it's much easier to use Tickle script to modify the clock constraint versus trying to modify the clock spec. Okay, so and you probably won't see the reason why. Usually, when you work on a design, it's much easier because you'll become familiar with the Tickle and also the command of the tool. It's much easier to do that way. So we go ahead and source this as is, and then we will modify it.
Anbach, we have a question that came in. Can you explain about the scan clock and the functional clock?
Yes. So let me ask that question. So in the design, your main clock, basically your function clock, which is your mission mode. That is your main mode where your chip's gonna function. It's designed to behave. That is where you're gonna be That's that's the main clock that will drive all the functional meaning that your mission mode, the way the chips are supposed to work. Okay, that's the main clock. It's called functional. You may have more than one functional clocks. Okay, multiple domain. The scan clock is for scanning. For scan, remember we talking about in placement. We're talking about the scan reordering, right? We have scan flip flops and scan mode. So the scan mode is designed for test, or DFT is served for that purpose, for scanning, for detecting defect, manufacturing defect. So it has a separate clock. So the scan clock usually run much slower than the functional clock. So you have a scan clock for the DFT purpose, and you have functional for the mission mode. Okay, so you're always going to have a scan clock and multiple functional clocks, your mission mode. So that's why that here we see a scan clock. Okay, so all your scan flip-flop in design, that part of the scan chain will be driven by the scan clock. Okay, and there usually a scan enable. There is a scan enable associated with those, and then when that enable, you in scan mode. When you that disable, you in functional mode. It's usually controlled by a mux. So that is the scan clock. So okay, so that's the base of it. So hopefully that explains the difference between the scan clock and the functional clock. Okay. Yeah, I did not add the describe the design details in the lecture. The lecture more about the concept. But you know, it's the scan, the DFT stuff is a little bit more is out of the scope of this class. So basically, we talk about the scan clock. I mean, the scan clock in terms of driving the scanner ordering. So I did mention those in the during the scanner ordering part of the placement. Okay, so that's the difference. Okay, so when we source this, so it took these resources C-cell spec, so it's understood the clock definition and so on. So here I had you guys I just noted the clock information here, but here I had you guys added additional. Let me let me move over so you can see the entire thing. So here we're using TickerScript to actually update the set target for the insertion delay. So here we set the target 1.0, 1.1. I believe this is to lose. We actually you can change this to something tighter. So I believe it's actually the clock skew was relaxed. The clock skew needs to be around 300. Okay, so this is how we set the clock skew for target for this skew group. Okay, so it's much easier than trying to modify the clock spec. Okay, so it'll take the last one. If you change your mind and you say, okay, next time I want an 800, and you can just change the 800 and reapply it again. So it'll take the last value. Okay. So here I'm just add additional strength. Here the skew targets is 80 picosecond. Okay, so that's updating it. Okay, and then in the next one I had you guys do the DRV rules. Okay, so we can set the notice this is CTS only applied to on the clock tree, right? Max cap, max transition time, max fan out. And you need to be careful what you set here. Okay, if you set the max transition too sharp, meaning that very strict, it's going to try to add a lot more buffers. And remember what happened with more buffers? It could lengthen your insertion lane, also increase your power, right? So, but when you work with design, you should know those things. You should get those spec from the designer, and also based on history. Okay, so now I have updated DOE rules and the clock insertion delay here. So these are the things that we added. Okay, so now we are ready. So if you want to know, is actually in this set, you can do a get DB here. You can do a get DB for any of the thing you just set, any of the. So you see a 60, right? So if you have Dow, you can check. Right, you can do those get DB. When you set DB, get DB is basically query the setting of those parameters to see if it's actually set. So okay, so it's set. So CC up actually is the command actually going to run the clock tree. Okay, so it's actually going to build a clock tree. This take a little bit, so I'm going to skip this, let it run. But I have a DB over here that's already been CC up. I think about like 10 minutes or so. So let me move to the next workspace that I have it's already been ran. But let me get the ticker script over. That happened here so slow. Bear with me, it's a little bit slow. Okay, so in interest of time, I'm gonna go to use my DB2, which it's already finished CT up. Okay, so if finished, you can do check floor plan and so on, and check plate to make sure it is great. So you can go through those. I'm not okay. So if you do have issue, here I include a command. If you don't have it's clean, you don't need to run incremental placement fix. Okay. If you have violation like the example I showed earlier, you can run place detail that's ECO true to do incremental placement. Okay, so once you do your check place again, okay. Here, I set the clock. It should have already been propagated, but this is how you propagate all the clocks. Okay, so once the propagation mean that you have real clock delay that actually is not using the modeling, the uncertainty and things like that. So it's actually lay and skew. Okay, so that's how I went ahead and have the command here that you can set the propagation delay. Okay, so let's report the clock tree. You should see similar to what I showed you earlier. So I'm just going to report it here. It's in that file. You can open it up, but here's the clock tree, the clock skew report. It's actually, yeah, so you can see, sorry. Yeah, so you can see here, it has all the clock source here. And remember the V, this is a virtual clock. So we have 1, 2, 3 virtual clock, which remember what virtual clock is? We discussed in last lecture, right? It's not a physical clock. It doesn't exist. It's just used for reference for constraining the IOs. Okay, so only real clock will propagate because it has real delay. The virtual clock don't. So you can see between the functional clock and the scan clock here, you can see it's propagated. Yes, the rest is no because it's virtual clock. So you can take a look at those. Okay, so and then here's the generated clock. So it's a multiplies divided by 2. Okay, so that's your clock information. And then I believe the next one is report skew. So I'm just going ahead and report this clock skews here.
Bach, before you move on to this, we have a request that you explain some more about the top, the trunk, and the leaf.
Top, trunk, and leaves. Okay. Hold on to that questions. Actually, in in the next couple of things, when we bring up the clock tree debugger, much easier because we'll have the clock trees there, much easier to talk about it. Okay, so Hải, hold on for a second, okay, for me. Um, so not sure why it hung. It should be relatively quick, but this something happened. Oh, this is not good. The network, so there's a lag in the network, a little bit slow. Okay, this seems to be, it seems to hang. Let me go back to the other DB, see if I have better luck. It's still running. It's routing the clock tree. So okay, let me go back to the other one. I may have to kill it and rerun. It shouldn't take this long. Something bad. Okay. Let me go and kill it, bring it back up because I really need the session to show you how to use the clock tree debugger, and that's one of the. Okay, yeah, I just killed it. Yeah, it's core dump. So this does happen from time to time. It's a software. It's a software, so it does happen. Okay, so it hangs, just kill it. Okay, let me get another shell. I did not anticipate this gonna core dump. See, we're 9 minutes left, so I'm going to go ahead and jump to the when I bring the DB back up, I'm going to jump over to the clock tree debugger. Yeah, my network is really slow. Let me go to workspace 3 so it's cleaner. Okay, let's just go straight to clock tree debugger. Okay, we talk about this. Okay, so let me here we start here. So once the DB back up, let's take a look at clock nets, and then I think after that we go to the clock tree debugger. Yeah. Was waiting for that. Is this one done? Maybe one's done before. Okay, so it's actually still running. Okay, while we're waiting, perhaps I can talk about the clock tree top and trunk. So let's see if they have, I think, okay, so let's, I have a picture here. Hopefully you guys can see it. This is the clock tree debugger. So the leaves, okay, the leaves would be, this is the clock tree debugger, the picture of the clock tree, okay. The leaves would be, the bottom will be the load, which is the clock pins of flops. Those at the very bottom we call the leaves. So it's like a leaf of a tree, right? On the tree, the leaves are the last thing. So we prefer these as the leaves, okay? So nets that route to the leaves are called the leaves, okay? The trunk are the main, these are the trunks, right? These are the trunk. The top will be these guys that driven by the buffer that from clock source here. These are the trunk, clock trunk. So usually when we put a clock trunk on the high speed design, we build a huge the trunk from the source all the way out to across. Let's say this is the chip. We build a trunk across like a spine across different area to cover the chip, and then put space out the super driver, buffer driver to drive those guys. So those are called trunk, and then those are called the top, and then trunk is thing that come out of it, which is the next level down. These are the trunks, okay, and these are the leaves. So hi, I hope that answer your questions in terms of trunk, top, trunk, and leaves. Okay, so you can have a lot of trunks here in between, but the top usually is the main spine that drive. Usually it's on the very top high level with the wide space and super buffers. Okay, this is very slow. So if that doesn't get done in time, you can pretty much follow the instruction to do the labs, because I have it's pretty details here. To look at the clock nets, I don't think you'll be finished in time. So once you pull up your design, right, you run through CS done, go through the report, turn up everything else, turn all the nets on, but then under the net section, make sure you turn all the layers and the routes on. So go on the net in this object window and just turn up all the net except the clock net, and you see this. So this only the clock nets will show up like this. Okay, so let me make it bigger. See, this is the only thing we get to use. Okay, so so here you turn off, make sure all the layers on, all the routes on, and on the net, turn up signal net, special net, ground net, just only thing on is clock net. You see these clock nets here. These are all the clock nets actually in design that is routed during CTS. Okay. And so let's zoom in. I had you guys zoom in to make sure and select one of the clock net, make sure that is the NDR rule is applied. So zoom in to select any clock nets and his queue to bring up the object attributes. And you just look at the router rule. You see the rule here. It's the 2W 2S. That's the rule that we created in the NDR earlier in the lab 1, right? We created 2WWS, which is double width, double spacing. So we apply to what's called clock route, right? So it actually got used here. You can see, you can verify it, right? So this is actually applied. And then you can see the width is 0.14, sorry. The default single space is 0.07 width. So you can see it's actually got applied. So you can verify that. So all the nets should have the same thing, the same width, double space, double width. Okay, you can so zoom in and click on it and to verify what's happening. Okay. Okay, so here I have you turn up all the metal set metal 4 and zoom in the area where there's usually clock nets. You can see it visibly. You can see it twice as big as this is the virtual route, the detail net. You can see it twice as wide. So it say on the object, it says it's 0.14, twice as wide, and you have to look at it as twice as wide. Okay, so time view. Okay, so for clock tree debugger, under the clock window, on the clock, this is CCL clock tree debugger. So you click on it, okay, and they'll bring up this configuration window. Just just hit OK, leave it default. So what it does, it bring up this clock tree debugger. It will show you, this is all the clock trees. This is the source, and this is all the buffers along the way, that different branches, and right, this is the leaves. So this is the graphical picture of your clock trees in your design. Okay, so when you say we have WWS, but I only see 2W clock path. Where you, okay, the 2S is the spacing. Okay, so the 2S, you can see the 2S is the spacing. Okay, so the 2S should be near here, right? So this is this is, you can see this is would be that should be on either side. There should be a space here like this. On this one is encroaching on this. This is single space. This is double space. So this is double spacing. Okay, so in this is a virtual route. Okay, so on the when the detail route come, this will be moved. Okay, if it has room, this will not be here. So on either side there'll be two spaces here. This is single space. This is double space. Okay, so if there's no space, to congested, the tool may put a single space here, but it violate the rules here. Okay, but your design has space. It should not. It should obey this where it consider DRC violation if this is here. But for virtual route, I mean, it was there before, so the detail route will clean all this up. This is just virtual route. Okay, so this is double space, two space. This is double width. This is two space. Okay, so when you're this is how you can tell. If you look at once the details done, you can see, make sure there's no either side. There'll be no there'll be empty space, no nets next to it. That's two space. Okay, good questions. Yeah.
And Buck, I don't know if you saw the final one about the two W2s. So where are the 2S, two W2?
Yes. So I just answered that question, Dave.
Oh, I'm sorry. I had some.
Yeah.
Wake up.
I just answered that question. So bring up this. Give me. Okay, so 11. Give me 5 minutes quickly. I think this is important. So when you bring clock tree up, it shows you the entire the clock tree graphically of yours, and there is a key window and control window. I think I talked about it here. Okay, so enable the clock browser. Okay, you turn that on. So you turn that on, the browser came on. This is in the clock tree debugger, right? So it bring up the path. This will be used later. Okay, this is it show you the clock path here, the worst case, and so on. So zoom in. This is the leaves. Okay, if you click on these flops, it will actually highlight and show you what cells it is in your physical view. Okay, so you highlight here, it will highlight which flop according to that flops. Okay, so you can play with this. And the keys, you bring up the keys, and the key has different things inside of it. It'll tell you, posi inverters and so on, what different things mean here, the legend. And then in the other side, okay, so this is show you, okay, so bring up the control, you click on this to expand, and this will have your different things in here. Okay, so let's take a look at clock tree. If you click on this, you can see the color code. Okay, so the purple one would be the generic clock. The red is my clock. Okay, and then so the generic clock should be small. Okay, and should be a lot less. And then you can see the test clock, the scan clock. Right, so different colors. You zoom out, you can see what clock trees is in. So you can play with that. And then you can also click the expand this. It'll show you different SKU group that highlighted. Okay, so here I had you turn all the color off, and then click on. You can change the color. You can highlight. Go back to the clock browser, and you can highlight the max path in red, and it should highlight. This is the max path in the clock tree. Okay, this is the math, and then you actually it show you also the corresponding path in the physical design. So here's the clock source. This is your clock path. You see what's happening here. Okay, so that's, you can play with the various things in there is available, different path here. Okay, so you can highlight different colors. You can see the min path, max path, or both path, or entire SKU group. You can click on it and play around. You can see the in the clock tree browser, and also you can see it in the physical view.
Okay, so I show you just a few there, but you can you have more time, you can play around with it and see the impact and what it does. But it's very similar to what I just showed you on the max path. The min path is the same. Okay, and you can play with this and you can see the hierarchy and the clock tree, the difference to group. Okay, and if you have like a negative and positive edge flop within the tree, it'll show you where it is also on this. Also, you have the multi-bit flops. Okay, and clock driver, all different things. So that is the clock tree debugger. We use that quite a bit to debug clock tree. Okay, it helps us graphically for those of you who like graphical. Okay, and also locations of this. So it'll help you in terms of, you know, if you have why your insertion is so long and so on, the highlight, and you can see why. Okay, and then I went do time report, pretty much similar to what we discussed before. So the clock tree debuggers is pretty much the new things. And then we already discussed about post-op. You can run that on your design. Okay, if you have issue, you have violations. Okay, I think the rest is pretty much self-explanatory. Just follow instruction. If you have question, feel free to send me email. Okay, so this is the end of my lectures for this class. In the next week, instructor Ting will take over. He will start with routing stage. Okay. So I appreciate all your time and your attention and also your questions. Yeah, but I'll still be around to support instructor Ting. If you have any questions or something like that, just feel free to ping me. Okay. Thank you all. You guys have a great
Thank you
day.
so much, Pat. Yeah.
Yeah.
Thank you.
Okay, I will be around support thing. Just like and feel supporting me or the rest of you guys.
Yeah, and also supporting the project, right? Coming up with all these.
Yes, yeah, work on
Yeah.
the project.
Thank you.
All right.
Awesome. Sorry
care,
for the
guys.
delays.
No
Yeah.
problem. I sped up. I think this the students should be able to follow the labs.
Okay. All right.
All
Thank
right.
you.
Bye. Take
Bye.
care.
Ừ,
Bye.
Bye.